שהוא...
חיברת אותו?
כן, אני מחובר. הוא על... איפה אתה צריך? הוא פה, הוא... אני במאה הרי. אני לא יודע למה, אבל בוא נראה. לא, זה לא זה. arrangement, mirror. זה אצלכם הבעיה, לא אצלי.
כן, כן, זה לא אצלך.
אוקיי.
איך מעבירים אותו למחשב? את יודעת? שהמסך יהיה מהמחשב שלו.
יש פה כמה לחיצות על כמה דברים. קורא גבר? איזה... בסדר. הייתי בסרטים, לא בטוח שהטייטל מתאים למה שאני הולך לדבר, אבל זה מה שנתתי לך בזמנו. נגיע לזה. רגע. שיט. איך אני עושה את זה? אני לא. זה יהיה הכי פשוט, אם יכול בפוקוס לסדר. אדם, אתה יכול לסדר את הפוקוס במקום שאני אתעסק עם ה... רגע. לא, תחזיר את הקודם, אני צריך שיהיה מסגרת. תחזיר שרופית. זה בסדר. אני אעיר אותך, אני בודק כל אחד, אחרת אני אעיר אותי.
Good morning, everybody. Today's speaker is Yuval from Rutgers University. Yair received his PhD at MIT Weizmann in '94 and did a postdoc in Lamont and a postdoc in Weizmann, and then joined Rutgers in 1997. He's interested in paleoceanography and paleoclimatology. Tomorrow, PAL seminar, there is no seminar. And next week, on Wednesday, we'll have Alan Gertler from DRI, who will talk about air pollution, sources, and impacts in the Middle East. Yair will talk about weathering effect on seawater chemistry during the Neogene. Thank you.
Good morning. I feel more awake than I am. To some extent, this is a deja vu and closing some circles. So those of us that are old enough, and I now belong to this, remember when was Lazar actually came back. I remember you got some prize and you presented your postdoc work on getting fluid inclusion. That was 1985, or when was it? When did you join? Yeah, I was a student sitting here, and it was pretty fascinating, the method and everything. I didn't think that 30 years later I'll get into this muddy water, but I'm glad. I guess we are closing the circle. I mean, I was so excited that I actually chose for my master exam to the exam on changes in seawater chemistry, read all the column book, so on and so forth. So I gave some talks over the last 3 years. I've been working on this project, and every talk that I give is completely different because obviously I don't understand everything. So this is, take it as a progress report more than, and hopefully thought-provoking talk more than a final product. Anyway, the simple thing, not that simple, was to come with a new proxy that we thought of, and it was a collaboration between myself and a few other people, Jonathan Harris, so it's an NSF-BSF project. And it was good, got me more reason to come here and talk. Other people that work, Agar Hauser did some of the experiment. Charlize Yu is a postdoc in my lab. Most of the work is hers, and Weizmann is another student that is finishing in my lab, and he did a lot of the mass accumulation rate that you'll see here. So what I'm going to do is talk about motivation, why study calcium in seawater. Then we'll have the proof of concept and practical estimates. Mainly to look at what's now we are calling distribution functions. Then I'll show you some record of about 40 million years of seawater record that we generated. Then we'll ask the question. Then we get to the really difficult thing, asking, why is it changing? What does it mean in terms of implication to climate, and mainly the carbonate and the carbon cycle, and then to climate, okay? And we have to tie it to the magnesium-calcium ratio of seawater. So, long time ago, Al Fisher back then published a paper where he noticed that there is changes in the mineralogy, predominant mineralogy of sediment, carbonate sediment in the ocean, and he kind of related it to what he called back then the calcite and the aragonite sea. So this is the Phanerozoic. We will be just looking at this part, but later on it was speculated based on this that it has to do a lot with changes in climate. So you can see ice house, greenhouse, and then related based on other experiments to the changes in the magnesium calcium seawater. Calcite sea will be when magnesium calcium is lower than 5, and aragonite is the more than higher than 5. Now, following some of the work that done by few people that were both in the Holland lab, and I guess Tim Levenstein was here and gave a talk, so I'm not even pretending to cover what it is. Eventually, there came a picture based a lot on fluid inclusion. Those of you that don't know what it is, it's essentially extracting residual seawater from halides and trying to reconstruct the chemistry when you extrapolate it back to what you think is normal seawater, which is, for example, based on chloride, in that case, and sodium that have a very long residence time in the ocean. And when you do it, you realize that the composition of other elements is different than in the modern, with the corollary is that seawater chemistry was different at that time. The basic thing that came out, just to show you here, through the Phanerozoic, major changes in the calcium going up, during the calcite sea going down, up, and then there is a big steep decline during the Cenozoic. And sulfate and magnesium, in this case we're showing only the sulfate, I'll go into magnesium, showing the mirror picture, and those, you know, that's what you would expect from keeping the alkalinity budget of the ocean at you know, not steady state, but a normal balance that you have here. Those are essentially the measurements, and all the rest is basically some sort of extrapolation that you have. The errors are pretty large, but also in the time. So what you see here, error actually only in the concentration, but we're not always sure exactly when the time. So we would like to have a method that we can actually relate the details to things like the evolution of climate. So this is, oh, terrible, sorry. But the bottom line, it's the 018 benthic formulae from 018 compilation of Jim Zakos. And the point that I just wanted to make here is that, you know, the Cenozoic, starting with the mid-Eocene and climate optimum, is a time that you have major change in climate, especially the Neogene. So if you look at the Neogene from, let's say, Nico, the mid-Miocene climate optimum, about 14 million years ago, you have a strong decline. So this is the Antarctic glaciation, this Antarctic glaciation, and then the Northern Hemisphere glaciation. So if you look at the, for example, what are we talking about? 1.5 per mil to about 4.5 per mil. 3 per mil changes in 018. If you take it just its temperature, it will be 12 degrees, but obviously there is ice volume. So the question that has been for a long time, over a century, was what's the control on atmospheric CO2? And by and large, and it started earlier by Chamberlain, but you know, Bob Berner, the late Bob Berner from Yale, kind of modeled it and brought the idea that there is a feedback balance between CO2 inputs to the atmosphere due to activity on the ridges and subduction, so related to seafloor spreading. Volcanism releases CO2 to the atmosphere. The CO2 in the atmosphere creates acidic rain that dissolves silicate rock. And this dissolution of silicate rocks essentially is transferring or bringing alkalinity into the ocean with other elements that you have here. That alkalinity is then precipitated in the ocean in the form of calcium carbonate rocks or sediments. But if you dissolve only carbonate rocks, all you did is just move from one place to the other the carbonate. Nothing happens to the atmosphere. But in the silicate, there is essentially mismatch or imbalance between the input of alkalinity and the output that results in a sink of CO2 into the ocean and reduction of CO2 in the atmosphere. The point that Bob Bernard did many times and sometimes in neglect is that it would take, without any feedback, it would take less than 1 million years to strip the atmosphere completely from carbon dioxide. You cannot do it. In the same way, if you don't have weathering, you'll get hot baths essentially very high. So there is a need to have a negative feedback, and the negative feedback is essentially atmospheric CO2. That will, high CO2 will increase the weathering, low will reduce the weathering, and of course that will be the balance that relates to essentially the seafloor spreading. I talked about that, 2 years ago. The competing hypothesis came in the late 80s by a group led by Maureen Remo that was just elected to the National Academy of Science, Bill Rodiman and John Edmond, and that was known as the uplift hypothesis. And the idea came from the fact that they noticed that really in the environment, modern environment, a large control on weathering rates, chemical weathering rates, is the exposure of fresh outcrop, fresh minerals. So you have to break new rocks, essentially, to allow for more intense weathering. And the idea, which was based on or supported by the strontium isotopic composition of seawater, it's hard to see here, but hopefully you know that, was that the uplift, the orogeny of the Himalayan in the Neogene essentially created this opportunity, so to speak, and because of the metamorphic redistribution of strontium between plagioclase minerals there, essentially what we got is strong weathering of the mineral contributing high strontium 87, 86 into the ocean. They did know and tried to deal with the fact that there is no basically feedback in this mechanism. So they realized, as people pointed out, that if you just go straight and that's all you have, there won't be any CO2 in the atmosphere. So they're kind of using records saying, well, there was some feedback. So this is carbon-13 showing a negative depletion over here, and they interpreted this less burial of organic matter or more weathering of organic matter. So those are two big kind of hypotheses that were there. I don't think they are really opposing because you need the feedback. Nevertheless, people have worked on that in the modern environment and other studies, and there is not much support to the uplift hypothesis other than the strontium isotopic composition and a few other things that I'll talk later. So I'm going to leave it here. Oh, please stop me, ask any question. I mean, it's fine. And just point out that, when they published it, actually, Bernard and Caldera modeled it quickly, and they show that if you just deviate a little bit from this balance, you are either, as I say, within a million, less than a million years, it will drive it either to complete depletion of CO2 or just going like runaway greenhouse condition. So, if you notice, this weathering brings alkalinity, but also calcium into the ocean. So we were trying in this study to look at the calcium in the seawater. So this is what we have for the Neogene right now, until now. Here is the calcium in the seawater, and this is the H. Those are the 2 points that we have from Yusuke Horita that measure them in the fluid inclusion. I think he followed the BOAS studies. I mean, I was fortunate to work with him at the Collins Lab, so I actually remember them working there. Those are the 2 points. And then other attempts by other researchers, Bathentel and Heuser, that use calcium isotopes in the sediments, essentially, to infer changes in the calcium of seawater. So it shows you what we have here, and you can see those have very large error and poor temporal resolution. And then the calcium, for reasons that I'm not going to get into them right here, are also having very large, range over here and kind of not very similar behavior in seawater. So now, a few years ago, I thought that we can address this problem in a new way. And the new way was looking at foraminifera sodium calcium ratios that can help us to reconstruct calcium. And the idea was that sodium residence time, oceanic residence time, is very long, about 100 million years. So in principle, if you measure any changes in sodium calcium in foraminifera, essentially that calcium has much shorter residence time, anywhere between 1 and maybe double that, 1 to 2 million years. The foraminiferal sodium calcium ratio should reflect seawater calcium. Now, this is kind of philosophically interesting. I mean, I was a student of Ed Boyle, and years before me, Peggy Delaney was a student there and did fantastic PhD, really fantastic. The sad thing is that at that time, for a reason that I'm not completely understand, she did not conclude on few proxies what now we know. So the first one was the magnesium calcium as a temperature recorder, which later I reanalyzed, and I don't think I was smarter or anything, but it took a while to get it. And here she also thought that both of the sodium calcium can be actually proxies for seawater calcium. They did the experiments, the culturing experiments with Alan Bell, the changes, only the sodium, not the calcium in seawater, and they got, for example, the planktonic foraminifera, no response. So that was the end of it. Actually, the data just was published, they never did anything with that. Prior to that, Dave Brown with Mike Bender also measured the whole Cenozoic. So this is sodium calcium, sorry, I didn't realize the quality was so bad. Sodium calcium in foraminifera, so this is from DSDP course versus estimated time, so 0 to about 100 million years ago. And notice they show a really big change in the sodium calcium. And they wrote that the most likely explanation is changes in calcium in seawater, but they didn't have the accurate distribution coefficient or transformation to the calcium and concluded that the changes are too large to explain by these things. This is from Peggy Delaney. She also saw down core record again. It's a multi-species. This is a multi-species of planktonic foraminifera. All of them saw that, okay? More recently, Yoshimura in 2006 did a crystallographic study where the sodium is sitting in the foraminifera and concluded that it replaces the carbonate species in the forum. So it's actually crystallographic trapped in the shell. Nevertheless, he took the same thing in the species of planktonic foraminifera. He saw this decrease over here and he said, this is diagenesis, so it doesn't work. I don't know how he got to this, but that was the situation when we started. So, of course, seeing that, right away, I called Jonathan and I said, Jonathan, we have to, test again this assumption. So we ran culture experiment. This was done with Laura Haynes, a student from Berkeley and at Lamont. And again, we're changing not for this. They did completely different experiment, but I measured the things for them. And if you look now at the changes in the sodium calcium, where we change the calcium, only variable calcium, not the sodium, you can see that for 3 species, the things that we see, all the species seems to be responding and decreasing with the decrease in sodium calcium. So there is a very clear response to changes in calcium in the medium. The second thing that you can see that, each species is slightly different. While the response is very similar, there are interspecies changes. So you cannot do multi-species, measurement, which probably was the problem with previous studies. Hagar with Jonathan did the same thing on the Pentica of Percolina. This is the lab right here. And again, they changed the calcium in the medium and grow those forums, and they get a really nice response that you can see here. In all these experiments, you can see that essentially the regression doesn't go through the 0. So many people kind of took the distribution coefficient concept. I'll do one measurement, I'll divide the forum by the water, I have the distribution coefficient. Wrong, okay? You have to actually change the solution chemistry. And Hagar and Jonathan really nicely articulated the difference between distribution coefficient and distribution function that comes of borrows the concept from previous study, Frank Hasiuk, David Evans that was working here, and essentially is fitting now a power function into this distribution. So you have a function. The physical justification comes from front-leg isotherms. So essentially we know now that a really important stage in co-precipitation of element into carbonate minerals is essentially the absorption on the calcifying surface. So that is justified. So now we have essentially the function for the benthic foraminifera and for 3 species of planktonic foraminifera. Now the problem is that it's clear that diagenesis could affect planktonic foraminifera, and I thought that it would be better to run benthic foraminifera that are less susceptible to diagenesis. And by the way, dissolution turned out to be the least of our problem. It's actually the overgrowth. So now that we use SEM on every sample, we know that this is the main problem. Anyway, we did a calibration and some preliminary studies. I think I showed these samples, so I'll run this data over here. I'll run through the data quickly. What we get is sample core top from many depths for a range of depths, anywhere from 400 meters to almost 4 kilometers, for 3 species. So we have here Euphigyrina, and then we have Wollastorfa, and also Oridosalis amponatus. I don't have the figure here. I think I showed it here. The point that I was driving here is that if you look at the depth transect, where we know the hydrographic condition of temperature, of carbonate, a lot of other things changes drastically, we see very little change in the sodium calcium of the foraminifera. There might be a hint, which we later have to deal with that, but not now, for some decrease over here. So my first conclusion or feeling was that it's really not sensitive to secondary effect. And in fact, when we ran about 160 kiloyears, so 160,000 years record from the North Atlantic, where we know that essentially climate, carbonate, temperature changed a lot, we see that 2 species, the Wollastorfa and the Euphigyrina, are flat through those major glacial and interglacial changes. So that was really good, and the other things that we knew from the work that we did before is that if you look at the data that we have for many of the cores for the late Pliocene, where we work on something completely different, we found that the sodium calcium in those 3 species during that period between 2.7 and 3.2 million years is about 25% lower than during the Holocene. So that led me to think that, here we have essentially effect of calcium. Calcium was slightly higher at that time. The question was, by how much? And that was tricky and still tricky. So after trying many options, basically I decided that the only way we can go about it is to try to use what we know, which the planktonic record, to calibrate essentially the distribution function for the benthics. So this is the work that Janni did a lot in different cores all over the ocean. And we are completely, aware that there are may be secondary effect. But here I'm showing you about 10 million years of calcium reconstructed from 2 species, Seculifera and Orbulina, using the distribution function that we developed experimentally. Okay, and then we fit the line into it, and where we have benthic foraminifera, now we have picked 4 type points. We have the modern that I'll show you, and we have 3 more type points over here that we have calcium from the planktonic. The scatter, I believe, those comes from different depths, different oceans, so I believe the scatter is partly made in dissolution. There is natural scatter. a lot of that. But I think this is the best that we could do to estimate what would be the distribution function for the two species, benthic species. So I'm using the sodium calcium from the calcium that I have here on this time point and our own measurement of the planktonic foraminifera. So this is here, and this is the measurement, and I calculated now the distribution function for those two species that we have here. So this would be Willistorfi, and this will be the Ombonatus uvigerina. The species, just so you know, that are different species. So now you take those and you apply it to the measurement that we did down core. Many, many, many measurements. I don't know, thousands of measurements. So this is what we have. And it's a work in progress. So what you see here is two species, Willistorfi and Ombonatus, using the distribution, the estimate that we have here, and plotted. So we calculated the calcium from the sodium calcium. So you have here the neogene and then the oligocene and so on and so forth. So what do we see here? Okay, we see first that there is a good, match between the two species. So to some extent, I can't say that I can tell you for sure that this is what we have, but I feel good that there is consistency, at least in those correlation. The numbers, the sodium calcium, are very different, so we got the distribution coefficient. The second thing, we are comparing it with the fluid inclusion that you can see here. Okay, so we clearly higher than what they have, but not by much given, and those are reduced errors that we have. The other feature that is really interesting, in my opinion, we have a period of stable calcium, and I'm saying stable, I'll show you in a second, I'll show the oligocene, so from the Eocene into the early Neogene or Miocene, so yeah. And most of the change, as we know now from other records, is essentially occurring during the Neogene. This is the time that, climate is changing dramatically, and we see that in the change in the calcium. Few other features that come to interest. One is, I'm not sure this is real or not, but this is associated with the Eocene, Oligocene transition. David Evans had work also and noticed that there is a drop in calcium at that time. So this might be real, but need a little bit more attention. Now, you probably also say, well, wow, this is all over, so what's going on? And I agree, this is all over. But luckily, this is actually a record that many years ago, earlier, that wasn't generated. So if you now plot the data, not as a scatter, so in blue, I'm plotting just the Oligocene, okay, over here. So from 22 million year to 34 million year, this is the data smoothed, okay? And you can see there is nice variability over there. And then I'm pulling.
Based on what? But this is your data.
Yeah, this is what I showed.
Yeah, what's the other one?
Wait, patience. So if you now filter this data with 1.2 million year filter, which relates to the 1.2 million year eccentricity that has been studied, essentially, there seems to be a correlation between the real data and there is a strong 1.2 million year that has to do with the eccentricity. So this is the Laskar solution for the eccentricity. I just pulled the 1.2. Of course, in this case, you have also other frequencies. So I'm not sure how.
Time scale is the same time scale.
Yeah, it's 22. Yeah, 22. It's the same time scale. So this relates to a paper that was done by. It's terrible, right? Or is it my eyes? I don't know. But anyway, Heiko Palicke, 2006. So this is unique record. It's a record in the Equatorial Pacific that really resolved the Oligocene, and we don't have many and nothing left from the samples, I think. But basically, Heiko published a paper where he shows similar variability in the carbon-13, and he said that the heartbeat consists of the 400, 120, 96, and the 1.2 million year obliquity cycles in periodicity, recurrent, blah, blah, blah. It showed that climate system response to intricate orbital variations suggests a fundamental interaction of the carbon cycle, solar forcing, and glacial cycles. Box modeling shows that the interaction of the carbon cycle and the solar modulation, deep ocean acidity, as well as the production and burial of organic carbon. So, I mean, I don't know if it's real or not, but I think it's kind of encouraging, which we'll see when we now discuss the mechanism, that maybe the calcium cycle, which should be tied to the carbon cycle, is responding also to much shorter variation than the long term that we have during the Cenozoic. I mean, it can't respond more than that. So now we get into the difficult, question is, what causing it? So what control calcium in seawater? Most of the calcium we get, the larger input is from weather, continental weathering, and then we have small from hydrothermal activity, and then, on average, as a box, it has to be some sort of imbalance. So how much you bring in has to go out, and it goes out mainly as calcium carbonate, or carbonate including dolomite. Very little, we can ignore it in evaporite. So the other implication is that we have a priori restriction on thinking about that comes from the saturation, carbonate saturation of calcium, saturation of the ocean, which is here, just to remind you, the omega, which is the calcium times, so the ion activity product divided by the solubility. Without getting too much into this, if omega was relatively constant and calcium was higher, then carbonate should have been lower, which has implication to many things that we think about climate. So a lot of work has been done over the years trying to test this stability of the saturation, and goes back to essentially let's reconstruct either mostly the CCD, the calcite compensation depths, which is now defined as where the rain rate of calcium carbonate from the surface is essentially almost equal, no, it is 20%, of the burial. So this is Van Endel reconstruction of the CCD, starting 100 million year to 0, and you can see that it's relatively constant, and then during the Neogene there is a small deepening that you have here, but it's about 0.5 kilometer. Another reconstruction comes from Heiko Palicki and Rich Schreier recently, and again, different reconstruction, but the bottom line you can see here that over the Neogene, so at hard for me even to see, I apologize, 30 million years, it's relatively constant, something about 4.5. You can see it very nicely over here. Okay, this has been now challenged by a group with Maureen Roimo. When they corrected the dynamic topography, they would argue that in fact there is a deepening of the calcium of the CCD. Nevertheless, it's less than 1 kilometer, and thinking about 15 micromole per kilogram on the carbonate per kilometer, it's really a small change that you have here. John Farrell did it many years ago for 4 million years, and basically his conclusion is that the CCD is relatively constant and the dissolution is essentially in the lysocline, in the area between the CCD. So the CCD doesn't tell us much about saturation. Going back to the first analysis that anyone has to do is just look at the cores. And when you look at the cores, this is a course from the Pacific at 2,500 meters. All of them look like this. Essentially, you look that they are, so this would be 5 million years roughly. Look how white they are, loaded with carbonate. And then started to get darker, 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 darker. So one place you'll say, well, it's dilution with the trickle. Another place, well, dilution. But when almost all the course going from white to brown, then something is happening there. So to test it, I challenged Weizmann, my student, to start to reconstruct mass accumulation rate. Because when I say that they kind of define what we think from the CCD, people say, well, you can't, that's impossible. Well, it's possible because the CCD is the balance or the difference between how much production we have, or rate, and how much is dissolving, and we need to reconstruct everything. So, to remind you, calcite, carbonate minerals are preserved on high, oceanic highs, so mid-ocean ridges and sea mountains. So this is where you get most of the production. This is 4% calcium carbonate with grade almost 100%. So look at this area. Really, on Tom Java Plateau, really high carbonate, this area in the platform. So we took transects through all those sites and essentially went to reconstruct the mass accumulation rate. But in difference with previous studies, we wanted to see what's happening there. So we separated the sediment into the coccoliths and the foraminifera. And the coccoliths are not very dissolution susceptible. They're really reflecting productivity. The foraminifera shells are the one that usually dissolve. So here's an example in the North Atlantic, for example, 14 million years. You sum those two is the total mass accumulation rate. But you see that the foraminifera, very little change we see, but the coccolith, notice what happened there, and boom. Very high accumulation rate, due to what we infer as high productivity of coccoliths. Same here. Same here. This is what's known as the carbonate crash. We're not sure why. But overall, during the early Miocene, where the CCD presumably was shallower, we have actually high production rates. The same thing you see in the Pacific. Very high. This is the carbonate crash. Not really, that's another topic for high over here, high over here. So everywhere, the foraminifera are really minimum. All the production, all the calcium carbonate is in the coccoliths, and we interpret it as high, essentially, production of coccolith at that time, decreasing toward the present. So this will be the white sediment, and then as they decrease, we get in darker and darker, less calcium carbonate. Now, you can look at that. And this is a slightly complicated figure, especially that seems to be out of focus. Oh, I needed glasses. But what you see here is the seafloor area that you have here, where most of that, and then the kind of change that you have in the CCD. So the CCD will be here, and each of them is one of the figure. One of the figures that I just showed you, this is a compilation. So this will be the early Miocene, mid-Miocene, and Pleistocene. So high accumulation rate decreasing, high decreasing. So and most of these happen actually in this area, in the area of the shallow. In the lower one, it's also the same trend, but everything is lower. Even though, so this one, 806, 807, 804, they're all coming from the same side actually, on the Java Plateau. If there was no dissolution, they should all look the same. So this is dissolution, the difference between here and here, here and here. So that's high preservation, high dissolution. If you look at the Pleistocene, the difference is not as much. In other words, as we say, the Pleistocene, the CCD might have been slightly shallower, less dissolution. You can see it over here. And again, the difference between here, that, and that is very large, where this one is relatively small. If you look at this now in terms of latitude, which is really important because you can argue that on those time scales, and I know I'm not going to get any, either we moved off the ridge or off the equator, so it's only a reflection of the continental shift that you have, or depth shift. none of that is validated because everywhere that we see the same trend. So I'll be happy to go through those data, but the conclusion is that mass accumulation rate of carbonate has decreased over the last 15 million years globally. And the question is, what happened to dissolution? Just as a preview, what does it mean that we have very high production rate at the Miocene? It has to be sustained by high alkalinity input. So there should have been high weathering, I don't know what, at that time supporting essentially the removal at that time of high mass accumulation rate. So we had to develop a new proxy for dissolution, and the reason is that the old proxies, they always measure the greater than 60 micron fraction, which is complete foraminifera relative to the whole calcium carbonate. The problem is that the whole calcium carbonate, so if you, for example, take it below 20, is a lot of coccoliths. So the coccoliths are changing, not the fragmentation necessarily. So we wanted to remove the coccoliths and then just look at fragment versus whole shell. So if you remove the coccoliths, you develop what we call coccoliths-free size index between 20 and 60 micron, and this is where you see the fragments. You can see nicely the fragments over here as compared. So this is a new dissolution. And in the interest of time, I will just give you, because I have, I guess, too many slides, but I'll give you the bottom line was that with this new dissolution, we can see really the shift in the coccoliths into less coccoliths as we go. But really, you can see, for example, if we take at the same time a shallow versus a deep one, the shallow is, you have high, let's see, mass accumulation is high over here in the forearm and decreasing, but the fragmentation rate, the new one, is getting better. So we're getting more preserved, less dissolution over here. So what do we have here? It's an antagonistic response, and you can see it here. High dissolution, improving, high dissolution, improving, same here overall. So to summarize, what we have now is antagonistic behavior where carbonate production in the surface ocean has decreased significantly during the last 15 million years. Okay, that's why we have less essentially accumulation of mass of carbonate, calcium carbonate. Yet the dissolution showing the other way around. So you come to think, wait a minute, I'm providing a lot of alkalinity to support so much production, how come we essentially have higher dissolution? So those of you that are not chemical oceanographer, the production of calcium carbonate at the surface is not, we don't know what it absolutely relate to, but certainly it's not a linear function of what's coming on. So whatever comes in, there is a lot more of the production goes to the down, but because you cannot maintain for mass balance, there is a compensation by dissolution back. So if you add those two things, the implication is that, you know, the production at the surface outpaced essentially the input. So the ratio between input and production was not constant throughout the neogen. It changes. Why? And other issues that we have to do with that. And that led to, even though you have, so you have a lot of ring, it depresses the CCD, that's fine, but you also dissolve a lot to make up for higher dissolution, for higher, production of the productivity. So if you want to reconstruct the changes essentially, which are important here, because we have to remove, as a weathering, you have to understand that essentially, as Farrell said, most of the dissolution is not really in the CCD, expressed in the CCD, actually in the area between the CCD, the lysocline and the CCD. So during the Miocene, even though we have higher dissolution, because of much higher production, we actually accumulated a lot more. So sediment. And the Pleistocene is completely different story. So this kind of confused us because we are thinking now about calcium. I thought, you know, as we go into the Neogene, into the Pleistocene, we'll have more input of alkalinity, and more alkalinity that essentially will lower the CO2. In fact, we have something slightly different, not slightly, completely different. Mass accumulation rate suggests that the weathering input of alkalinity and calcium decreased from the Miocene in the present. Did not increase as, for example, the uplift hypothesis would suggest. So now we don't know if it's silicate or carbonate, and that's something that we need to address. So in the next few minutes, I'm going to go back to the different hypotheses and try to make sense. Well, I'm sure I'll fail, but anyway, here is the CCD, not much change that we do. Here is another CCD, but by and large, you know, it's relatively constant. This is the strontium isotopic composition that we still have to explain. Why is it increasing? And then just remind you the carbon-13 record. Now, we have another line of evidence to confuse us, and that's the lithium isotopes. Lithium isotopes comes mainly from silicate weathering. And just to make it simple, you have the delta lithium 7, and when you get, let me see, when you get the light seawater in lithium isotopes, okay, that means that all the weathering product from chemical weathering went to the ocean. The way to make it heavy is by keeping the light isotope actually in the weathering product. That means that you have an incongruent dissolution, and the lithium-6, the light one, is absorbed onto the clay minerals. So the work that has been done shows that there is a very strong trend toward heavier lithium isotope, more lithium-7 that you have here. So this one is a complete weathering, congruent weathering, everything goes to the ocean, whereas over here, the Neogene that we have, we start to get a shift to the isotopic composition that suggests a strong incongruent weathering, which we wouldn't interpret as we, you know, the Himalayas is rising up, the cold weather, all the physical mechanism there increasing essentially physical weathering, but because it's cold, we don't get as much chemical weathering. The idea of marine was that those products of the physical are going all the way down, and then in the lowlands, essentially exposed to chemical weathering. Well, the accumulation rate in the Bay of Bengal are enormous. Those things are stayed as a physical product of weathering. So, just to wrap it up, I don't know how many minutes we have. Do I have 5 minutes? Yeah. No. What's control with? Forget? Fine. Okay, I'll speak faster. But anyway, we can then bring also the magnesium calcium. We have to bring it into the calcium. So those of you that don't know, the magnesium and calcium also have antagonistic behavior. They're exchanging mainly in hydrothermal events. So magnesium, as we get high, you know, spreading rate, so to speak, magnesium goes to zero output into the ridge by seawater rock interaction, and calcium is released. We have the mimetization that I kind of think that you can have exchange over here. So there should be some, or we think that you know, in order to change the calcium of the ocean, you also have to change the magnesium. That is to maintain the alkalinity of the ocean, but also think about that. Every time the calcium comes, you know, into the ocean, we will remove the alkalinity. The only way to do it if you exchange it with magnesium, and that won't unless you precipitate dolomite. So here's the magnesium calcium of seawater over the last 160 million years, with increase, very sharp increase in this. We show that in the last 20 years. The record comes from different archives. By and large, I think we may be arguing what exactly it was at one point, but there is a strong increase at that time. Okay, so we know now that magnesium is increasing when calcium is decreasing. And what can affect it? Seafloor spreading rate, the hydrothermal activities that I just mentioned, decreased aromatization, increased weathering input. So we don't consider that in the neogene as really important. In any event, it's a small flux. So it really has to be between those two that we have. Now, the spreading rate is huge. This is, now I'm stepping beyond my expertise. Now, before that was my expertise, but you know, the kind of canonical over the last several years coming from Dave Rowley, but even before that, was that by and large, over the Phanerozoic, and in this case it's just Mesozoic to Cenozoic, the spreading rate were relatively constant, okay? So this is the spreading rate. This comes from the compilation of Dave Rowley's that you see here. Obviously, there are small changes, but nothing that consider on the long term as really changing the load. So if you take this at face value, you would argue that maybe weathering or changes in spreading rate, this is spreading rate, sorry, did not affect the magnesium, calcium, and the calcium of the ocean. So one thing that you can do, and clearly what we've seen from the changes, for example, in the Oligocene, that there is that the calcium concentration of the ocean is not in balance. It was maybe balanced during the Oligocene and Cretaceous, where there were not much changes. So you can do some small changes in the input, for example, of weathering, or maybe in the hydrothermal that I'll show you, that change essentially the ratio of magnesium, calcium, and alkalinity. So you can essentially change the type of rocks, either in the weathering or in the hydrothermal activity, that will change the balance in the seawater. So I want to finish here, and this is two things. One is a paper that came, I can't remember, a few years ago by Marco Ligi, that essentially attribute the changes in seawater magnesium calcium essentially to the change between, or the shift from fast spreading center to a slow spreading center. And their idea was that essentially you change, due to this, the interaction with peridotite that are really rich in magnesium, sorry. So again, the idea was that decreased spreading rate, essentially increased hydrothermal input and decreased hydrothermal output that you have by changing changing from fast reach to slow reach, and the rate of that, they will argue, of spreading essentially will determine the melting of the mantle of the seawater interaction. In the interest of time, I just want to finish and then we can talk. So, two things, final formula for our summary: sodium and calcium can be used for high resolution seawater proxy. I think we can get the calcium. I'm sure about that. That's no, so we fulfill our mission. Then our real challenge will be to try to explain what does it mean in terms of the mechanism that are completely global mechanism, okay, and for climate. I would say, regardless, as a final conclusion, regardless of you know, whether we know exactly why it happened, the fact that the ocean saturation did not change dramatically. It did change, but not dramatically. But calcium more than doubled itself. Implies that, you know, we have actually a negative feedback when you have high alkalinity input, as we saw. In fact, the alkalinity of the ocean is lower. That's when we see the dissolution. The carbonate ion is lower. And the ability of the seawater, since they are more acidic, to buffer CO2 is compromised, is decreased, which would be consistent with higher PCO2. As we go, so here's a modeling of this calcium, effect of calcium of the saturation. You can see that the carbonate is increasing, as we argued during the Neogene, nicely, and that's mimicking essentially the calcium. So there seem to be some feedback there. They're keeping the alkalinity despite the changes in the erosion. I'll finish here and maybe there are questions.
Two time scales in calcium. One is to show and maybe from two different reasons, because there is a long-term change you saw from the Mesozoic to present in calcium. And there is this 1.2 million years, which is completely, maybe
totally
you have to start maybe with this one because it's
totally
important. So, so
totally
there is some links. Also in the mechanism that you explained, maybe one is related more to the short term.
So I think that I absolutely agree. Yeah, so I think that the short-term variation has to do with weathering and changes. Clearly, for the long-term, there are different control. I'm not sure what, but I would be inclined to accept the hydrothermal exploration more than the weathering. So I was doing that. I just don't know right now how to nail down one from the other. Mary.
Maybe two questions. One, the decrease, the rate of decrease in the calcium roughly correlates with the northern hemisphere appreciation. Is that correct? If there is any connection?
Well, it started earlier. It started about, I would say it started about 14, 15. Anyway, we don't have the exact. So earlier than the classic 2.7, yeah.
And what about circulation?
Ocean circulation?
If we increase the ventilation, it affects the calcium?
I don't think it affects calcium at all. Circulation. That's, say today.
But on the CCD effects?
To what class are you now? You are confusing two time scales, okay? For the short time scales, absolutely, the compensation, but on the longer million years, you look at this as a box. Whatever comes in has to go out, and if there is any imbalance, it will determine the sensitivity. So I don't think ventilation has, it will affect, difference between one core and the other, yes. But that's why we went and did many, many cores. Yeah.
Thank you very much.
You don't have a question? לכולם, נכון. כמה שיותר יותר טוב. רגע, תהיה מגן. אני טוב. מאיר, מה שלומך? ברוך השם. ברוך השם. איפה יודע? לא, אני יודע. אם זה נכון, לא, אני מסכים. אם זה נכון, צריך להסתכל על זה.
כמה זה, אם אתה מסתכל כמה סבוך, אם אתה עושה אינטגרציה לעולם, פלקסים פרמונל עכשיו, מהפלקסים שאתה ראית במסה במולה שלו, אתה רואה, אתה יכול לראות איזה שינויים זה עושה בכמות הכללית של קלציום באוקיינוסים, לא מדבר עליו, עכשיו זה כמות כללית.
בקלציום נורא קשה, הוא הכל נדבק, בהתחלה חשבתי ש...
לא, בזמנים הקצרים, דווקא
בזמנים הקצרים, יש לנו... לא, גדולים מאוד,
אז זה צריך לעשות שינויים בריכוזים, זאת אומרת, צריך שינויים בכמויות שצמורות באוקיינוסים.
ב-12:30 אנחנו נפגשים במזכירות,
ללכת לכל צהריים. בסדר?
טוב, זמנת.
איתה גם, כן. אנחנו רוצים לדבר איתו כמה דקות.
יש לי שריפה בבית.
יש לה שריפה.
לא פיזית, עם הילד.
הילד.
איזה?
השני בן 16.5 בעוד גיל ההתבגרות.
מה השריפה?
נפלט מכל המסגרות, אנחנו רוצים לעשות משהו חדש.
רוצה להיות חופשי.
רוצה להיות חופשי.
תן לו להיות חופשי.
הוא הכי דומה, כן, זה מה שאני מנסה לעשות, הוא הכי דומה
אתה
לבית שלו.
עשית מעבר אחד, למה אתה לא תיתן להם לעשות? אתמול ישבתי עם אחד שעשה את המעבר השני, אתה לא מכיר, הוא גר עם הבת שלי, והוא אומר לי, תשמע, אני, תואר ראשון היה לי מאוד קשה, לומד פילוסופיה. לא הפסיק לשאול אותי שאלות, לא הפסיק. שאלות אדירות, אתה מבין, מה שאתה מחפש מאינטלקטואל. הוא שואל את עצמו אם הוא מתאים לאקדמיה, ואני אומר, אתה לא רואה? אבל הוא אומר, הייתי צריך ללמוד את הכל, לא למדתי כלום. אז אני בדיסאדוונטג' אמרתי לו, כן, אבל יש לך את האדוונטג' שבישיבה אתה לא משנה.
חשוב.
לא שזה אני לא יודע,
זה
משמעת לימוד אדירה, וזה החלק שלי, זה יותר חשוב במשמעת לימוד.
מה זאת אומרת, שותף של, או בן זוג של...
לא, הוא שותפים לדירה.
מה שרצינו, רק אני אגיד בראשי תיבות, יש רקורדס טובים מאוד, מאיר חושב, של
קפריסין.
כן, הזויקון בקפריסין.
אני הייתי בקפריסין, אני מנחש הכל. הוא אמר לי.
רוח הקוטג'.
לא, אז השאלה היא אם...
איפה זה? באיזה אזור של קפריסין?
השאלה אם של הטרודוס.
כן, של הטרודוס.
לא.
מלחך את הטרודוס.
אבל זה שם, איך זה עומד? זה אופקי, זה...
קצת
זה קצת טילטד, הוא אומר, זה הכל. קצת טילטד זה בסדר. השאלה היא כמה זה genetically altered, או אם זה באמת שמור טוב. אתה מבין? זאת יש.
חיבור את המכשיר איתה.
בסדר, אבל אנחנו יכולים לדבר על זה.
טוב.
אז?
באימייל.
צריכה משתובב מאוד לתת הרצאה.
כן, אבל היא לא מסתובבת מסיבות...
פתיחה, רכסים, ואז מחיתה, ואז שתשתו ישנו ביבשה.
כן, זה גם...
האם יש קשר בין קצב הפתיחה לבין קצב שחרור שניים?
זה הטיעון הכללי. עכשיו, השחרור שאתה מדבר בסבדקשן, תלוי במה...
שאתה יראת, לא שאני מדבר.
לא, אני יודע, כן. מה שאתה שאלת, מה שהולך בסבדקשן, כנראה גם תלוי במה אתה עושה סבדקשן. אם אתה עושה סבדקשן של נגיד קרום עם סדימנטים קרבונטיים, והתוצאה של הקרמליה, שאני זוכר עוד מסירת המשחרר סירתו ברמות, אז נניח יש חבר'ה שטוענים שבאמת הסירתו היה גבוה באיוקן, כי אתה פשוט את כל האזור של הטטריס.
אני לאחרונה שהתייחסות היא לא נסכם לקצב של הפתיחה ולכן הסדקשן, אלא גם תלוי במים הסלעים.
זה גם נכון בספרים.
השיניים זה עדיין...
כן, אבל איך אתה מכמת את זה? אני לא יודע. מכמת. לא, אתה
למדתי ממנו את התכנון.
מכמת, כן.
כמו לביית.
לכמת. אני לא יודע. הראיתי גם מה האינטראקציה, ההנחה שזה רק הקצב של הוא גם לא נכון, הקצב שלנו. לא יודע, צריך לחשוב על זה. מה שחשבתי זה על פוטסים, מה זה שלו.
זה בדיאגרמות שונות, אבל לא ראיתי את הקשר ההדדי בין מה שאתה מחשב, אתה לא מודד את הקלציום. אתה מודד בבנטיק, ביחס לקלציום, ומניח שאתה יודע שהסודיום, שהוא לא השתנה. האם יש קשר בין הדברים האלה לבין ה-PCO2? נניח בין ריכוז הקלציום לבין...
זה מה שהראיתי בסוף, שכשהקלציום גבוה, בגדול הסטורציה של הרוויה של מי הים לא יכולה להיות יותר מדי גדולה, כי אחרת ה-CCD היה מגיע, אתה יודע, עמוק או למעלה, אז אתה יודע, אתה מדבר על נניח חצי קילומטר, זה לא הרבה. אז במובן הזה, כשאתה מעלה את הקלסיום, אתה חייב להוריד את הקרבונט. כדי לשמור על האומגה. CO3, כן, את הקרבונט, איון הקרבונט. אתה מוריד אותו, אז נניח במיוקין הוא היה יותר נמוך, ואז זה חייב להיות קשור ל-CO2. אז זה מעניין, כי באותו זמן אנחנו גם יש לנו פלקסונל קליניטי מאוד גבוה. זה מה שלגמרי שיגע אותנו. אנחנו ציפינו בדיוק הפוך. אני תמיד חשבתי, קלציום גבוה, זה יהיה CO2 עם אלקליניטי גם במים יותר גבוה, אבל זה מה שאומר שהאלקליניטי הייתה יותר נמוכה, כי הקרבונט הייתה. אבל לא בטוח בדיוק למה, אבל זה כנראה, זה צריך להיות דרך הקומפנסיישן.
זה פורסם.
זה צריך להיות מפורסם, אבל עד שאני אבין לגמרי את ה... אנחנו נשב, לא, יש מאמר אחד של הגר ויונתן, שרק הקליברציה, יש מאמר שאני יושב כבר 2.5 עליו, אבל הוא יפורסם, אנחנו נוציא את הפרסומים בחודשים הקרובים.
אם לא קשה, אתה יכול לתת את זה, שמעת הרפרנסס שהזכרת פה
אני אעשה את זה. אני חייב להגיד שהרבה מהפיגרס האלה זה לא אני. זה הסטודנטים.
תגיד, המחזורים האלה של המגנזיום, שהראית המגנזיום והקלציום, הרגונית, קלצית, זו נשאלת בהתחלה. ניסיתי להשוות את זה, ניסיתי לראות, לבדוק עם המחזורים של פלגי ההתבדרות וההתכנסות של היבשות,
מה שנקרא ווילסון סייקל.
ניסיתי לראות אם זה קשור? נגיד לך מה המחשבה.
קודם כל, אני לא עבדתי על כל הפנרוזויק, אבל המחשבה היא כן, יש הרבה, שהתנאים הקלימיים, תנאים בווילסון סייקל.
כי ברגע שיש לך פלגיה כזאת, אז יש לך פחות אירוזיה בעצם.
בליה, אירוזיה לא, לאף אחד לא אכפת מאירוזיה, בליה היא חשובה.
כן, סליחה, בליה, נכון. יש לך פחות.
כן, כן.
מן הסתם זה הוריד לך את הקלציום.
נכון. אז לא, אבל זה לא רק פלגיה.
כי המחזוריות היא דומה.
זה נכון.
ה-wavelength, ה-cycles, דומים.
נכון. אם אתה מסתכל על הדברים, אבל אתה יודע, זה לא, זה דבר, קודם כל, קשה להשוות בין מחזורים שונים, כי המחזורים שני האחרונים, יש האבולוציה של צמחי יבשה, אתה יודע, דברים משתנים, אז אתה מסתכל על...
התפתחות משתנים.
אתה מסתכל על הקרבוניפרום, בום, CO2 לגמרי. אבל אני מניח שבגדול זה כן, המחשבה שזה כן משפיע. הדבר המעניין, אתה מתקח למשל, ואז חשוב שלמשל המים קובע את הקלצית הרגונית, אבל באופן כללי, למשל דברים כמו אלמוגים, הם גנטית מייצרים הרגונית. הייתי נמצאו כמה שהם קלציתים.
לא, אבל יש
הוליסטים,
שהם לא קשורים לזה האלמוגים. הם מגיבים על...
בעצות, הגירניות. בעיקר בשלבים האלה שרוב ההשקעה הייתה, אתה יודע, בים רדוד. אז הם נשארים. אל פישר היה בחור חכם.
מאיפה?
אל פישר הוא נפטר, אני חושב התחיל באוניברסיטת קליפורניה ואחר כך עבר לפרינסטון או הפוך. היה לו גם, הוא מאלה שגם מהראשונים שדיברו על ה-KT extinction והבולה אצל, הוא עם הרבה רעיונות. אני לא פגשתי אותו אף פעם. מישהו שכח שלך, זה אתה? טלפון שלך?
לא.
שכח טלפון.
זה שלי.
לא, שלך?
אני אצלך.
מישהו יבוא. הוא טוען אותה.
מה? מחר אני פורס לך את המוקם ליבוקם. זה חדש, אתה לא מכיר כלום.
בסדר, אני מחכה, יותר מדי זמנים, אני לא חכם כמוך, אז דיוויד אבנס, יש לו, הוא עשה בדבר אחר, שגם כן הוא טוען שהוא רואה ירידה בקלסיום.
ככה זה נראה, יש שם איזה דיוק כזה.
אתה ראית? לא, אצלי.
כן.
אבל הוא, יש לו מבית תקפור אחרים, הוא רואה גם כן את זה.
את הירידה.
את הירידה, כן.
ולמה יש ירידה?
הוא טוען שהירידה זה בגלל שיש לו השקעה שהיא גדולה. אני לא ראיתי את הדאטה, הדבר הראשון ששאלתי אותו, האם זה חוזר מיד. אתה לא יכול להוריד יותר מדי, ברגע שאתה מוריד, אתה מבין, כי הקלציום יש לך 10, אז 20 מילימול, אבל קניתי אתה 2 מילימול.
כל פעם אלקלין, כי הייתה נמוכה מקלציום.
כן, תמיד, ועוד כנראה יותר נמוכה, אז אתה לא יכול להוריד. אבל אני חושב שמה...
היום זה כמעט פי 10.
פי 10.
2 לעומת 20.
לא, 10.
לא, 10. לא, מיליק ביניהם.
במיליק.
וזה 20, זה 20 וזה 2 בערך.
אבל אני חושב שמה שקורה, ואיך אתה זה שאתה יודע, אימבלנס קטן בכמה אתה מביא קלציום לבייקרבונט או לאלקלין, זה מה שיכול לשנות בסופו של דבר. קלציום, מגניזיום, ואתה חייב להחליף קלציום ומגניזיום, וכמובן הסולפט. חשבתי שיש לנו סולפט, אבל וגם מראה את הכיוון ההפוך. נראה שיש משהו אחר שמשפיע עליו.
שמוריד לא, אבל למה אצל אבנס?
הוא טוען, שבאותו, בזמן הקצר הזה של היוסין או ליגוסין, אנחנו יודעים, יש ירידה של ה-CCD, ואז הוא טוען שיש השקעת יתר של קלציום קרבונט, שמוציאה את הקלציום מהפלנוס.
אפקט מקומי כזה בזמן.
כן, אתה לא יכול לעשות את זה יותר מדי ארוך.
פאליקה, דרך אגב, מה שכתבת פאליקה, כל הדיאגרמות של הסאבסידנס, זה 2012.
מה כתבתי?
2010.
כן?
זה קופץ ישר לעיניים משפיע.
זה לא אני, זה הפיננס שלי כתב, אני ישר מפטר אותו. אני לא, אני הייתי צריך כל בעיה לעשות את הסמינר בזמן, כי לימדתי.
קיבלתי הערה מקן מילר, אני חושב שזה קן מילר, רביו, שלא ציטטתי אותו.
לא אמרתי כלום, אני לא יודע.
אני כאילו בטוח שהיה רביו, לפי הארגומנטים.
אוקיי.
טוב,
יש לך שאלה?
כן. תוכל לשלוח לי את זה
את הרפרנסים? בסדר.
למייל שלי.
יאללה, סלמת.
אנחנו נראה אותך מחר, אתה אומר?
בעזרת השם.
קנית את הסיפור?
קניתי את הסיפור מעניין, וזה עורר אצלי כל מיני מחשבות. מגנזיום וקלציום מבחינתי זה מרכיב חשוב. בדרוויטים. אני אתמול הייתי בסיור בכרמל,
היית איתם כן, אני תמיד זוכר את האפייה של הקלציום קרבונציה, זה בדיוק מה שקורה כתוב בסדקציה, אתה משחרר הרבה סרטים.
מה שזה חשוב, איך נמצאים התאים המגמטיים שמשחררים את ה-CO2.
כן, זהו.
אני חושב שהולכים לבולקניזם.
נכון.
אם הם נמצאים בקרום הסדימנטרי,
אז זה מה שהראיתי שם עם הפרידוביטים.
אם הם נמצאים עמוק יותר, אבל זה לא. שזה לא
אבל זה בדיוק.
קצב יותר גדול גם.
אז זה לא היה לי זמן, כי גמרתי, אז רצתי, אז זה בדיוק המעבר מה-fast spreading to slow spreading reach, כי זה קובע כמה פרידוביטים הם קרוב או רחוק מהקרום. לגמרי צודק. אבל זה הכל במודלים, הם עושים את זה.
כל העסק הזה זה מודל קלקוליישן קלציום.
לא, אבל המדידות, הקלציום, אני בגדול מאמין לו עכשיו, השאלה אם זה היה 20 מילימולר או 25 או 30. אני חושב שברמה הזאת, ככל שיהיה לנו יותר נתונים ונצליב אותם דרך דברים אחרים, יהיה טוב. אנחנו, לא יודע, היה לנו איזה... זה טוב שהייתי צריך לתת את הסמינר, הייתי צריך לחשוב.
יש לך זמן לחשוב, רק עובד, תקתק.
קודם כל אני נוסע, ואני מלמד, אתה יודע. יהודה, אני פה עוד כמה ימים, אבל נוסע. יהודה אנזל בהרגשה שהוא עושה לי טובה שאני בא ללמד פה. רציתי להסביר לו שזה בדיוק ההפך, אבל אני אפילו לא מנסה. שבוע כזה הייתי יכול לשבת ולעבוד, אבל זה בסדר, חלק מזה זה כל ה...
רגע, מתי אתה נוצר?
אני עושה יותר מדי, גמרתי.
גמרת?
עושה יותר מדי דברים. אני אמור להפסיק, וזה שבתות, יותר מדי.
אתה בשבתון?
אתה
בשבתון עכשיו?
לא, לבית, אבל שנה הבאה.
איפה?
אתה יהיה קצת פה, קצת שם, לא יודע, לא שנה הבאה, זה או בקיץ, אני חושב, תלוי בהפלגה שלי במאי, אבל...
מה בהפלגה?
יש לי הפלגה בדצמבר לדרום צ'ילה, ואני מחכה לראות אם ייקחו אותי על ה-ADP ל-ACC. זה עוד דרייק פאסג' וזה תהיה הפלגה.
דרום צ'ילה, זאת אומרת, זה ממערב לאמריקה או ממזרח לאמריקה? איפה זה הולך?
פציפי.
התשובות שלי של איזה אוקיין.
פציפי.
אחר כך תסתדר.
פציפי. בצד הפציפי.
בשביל דרייק פאסג'?
לא, זה אנחנו עובדים על האינטראקציה בין פטגוניה לאקלים. לא הייתי בפטגוניה, אז כתבתי הצעת מחקר, אבל בפטגוניה. זה הרעיון. תמיד אני אומר את כולם שהייתי מדריך טיולים, אז יכלתי לטייל, היום אני לא, אז אני מוצא הצעות מחקר, כותב, איפה שאני רוצה להיות.
זה מה שאתה מקבל אותה, זה לא לך לעשות. לא כל אחד מקבל, כמו שאתה יודע.
זה נכון, אבל שמחתי אני overfunded.
תודה, בעיה.
טוב, יפה.
מה זה? כן, זה צריך יותר, זה דבר מחשבה הדבר הזה.
מה שחשוב זה סטימולטים, זה הכי חשוב. בינינו זה הכי חשוב.
כן, והחבר'ה שעובדים איתי הם על הכיפה. בעיקר זה שעשה את הסיני שעשה את המס accumulation rate, הוא באמת בחור מבריק. הלאה.
עוד סיני מבריק. עוד סיני מבריק.
איתן, כיף לראות אותך תמיד. כן.
העבודה שלי על סקלות זמן אחרות לגמרי, רק 1,000 עד 1,000 וקצת שנים, אבל הסודיום זה אחד האלמנטים שראיתי בו, הערך הסודיום לקלציום בפרמיטידים, זה אחד הדברים שבכל הים התיכון אני רואה סיגנל ברור, ולא הצלחתי לקשר אותו לשום דבר. בכולם יש עלייה ביחסות עם הקלציום על פני התקופה הזאת.
מה, זה 1,000 שנה אתה מדבר?
1,000 שנה, כן. עכשיו זה בים התיכון, גם המערכת שונה וגם החיה היא אחרת. אני לא יודע באמת אפשר...
תראה, יש עבודות שטוענות שסודיום, קלציום משקף מליחות. וזה, בחלק מהדברים זה נכון.
אבל לא סביר שיש כזו עלייה של מליחות.
אני לא יודע.
ב1,000 שנים, זאת אומרת, כמו שאני ראיתי. זאת אומרת, זה לא יכול להיות רק זה. ולפחות בקורטופס שלי מ5 מקומות בים התיכון, זה לא משקף את הווריאביליטי של המליחות בים התיכון. אז יש עבודה של גיליקין על אלמוגים, על סודיום וקלציום באלמוגים, אבל גם הוא לא מראה פרופיל לאורך זמן, אולי כמה עשרות שנים. בסוף הוא מסיק שהוא לא יודע מה זה.
לא מכיר את המאמר הזה.
הוא פוסל שם מליחות, הוא פוסל שם טמפרטורה, הוא פוסל שם נדמה לי גם ריכוז קרבונט, ולא מוצא מה זה כן. אבל סקר הזאת עכשיו, לא יודע מה באמבטיה של הים התיכון יכול להביא לשינוי בקלציום בסקלת זמן כזאת.
טוב, אבל אלה חבר'ה של גאות ושפל, לא אורמטידים.
נכון, אבל בסך הכל הם נחשפים לים מעורבב, ביחס לרוב האלמנטים.
לא יודע, לראות את הדאטה קשה, אבל לא בטוח שנדע גם עם הדאטה, והוא לא סופרלציה עם שום דבר אחר, אלמנט אחר.
לא, ממש, גם כשעשיתי PCA לכל אלמנטים שלנו, אז הוא עומד כמעט לבד.
האמת שאני לא יודע הרבה על ורמטידים, אז מה זה בכלל? זה תולעים? מה זה?
השם שלהם הוא בגלל שפעם חשבו שהם תולעים, היום יודעים שהם מולוסקות.
מולוסקות?
זה עדיין שגם קריאה שלא מעניין את הכלל.
תשתע.
מודיעים היום מעניינים
נשאיר שם, ולא ככה היום.
עוד נוער ראשון, הולך כדי...
אבל תשב על השולחן שלו.
לא יש לנו דברים.
כן? אוקיי, בסדר. מה קורה? מה היה במתמטיקה?
החלק שלהם בסדר, זה בעיית מיומנויות. מותר לזה בכיתה, נראה לי שאני יותר כמעט על הכל שלו נכון.
רגע, מה העיבוד האחרון? הייתה עבודות? הייתה כבר עבודות? מה זה? תראה, שסגרתי תשובה, כל כך מוקדם, זה לא מאוד בעיבוד.
יש לי עכשיו שבו באזרחות, שבו עובד בהיסטוריה. זה לא מדבר, בעצם...
אז לא הלך, לא משהו.
אז היא חבר'ה שזה בסדר, כאילו, לא עשיתי גם טוב, אני מקבל כל הנקודות שלו, אני מקבל 60. לא צריך לעשות את הגיאומטריה. זה לא נפרד לך. אתה מציץ, אני אומר... טריגון. זה היה שטריגון, היה שמה של גיאומטריה. זה נבחר את זה לטריגון. כי יש שם משפט שעברתי בגיאומטריה של גיאומטריה. אז עברתי לטריגון. ועשיתי חישוב, חישוב. סתם מה? אני מכיר, ואז חשבתי שהדרך שלי לא נכונה, אז ניסיתי עם זו דרך אחרת, לא מצאתי, אז נקע אותי, ושאני נקע אותי, והגעתי מובעים. אז לא יודע אם אני אבוא.
אבל נשמע שזה הרבה יותר.
כן, אני שמוע בעצם שאתה לא יכול.
בסדר. אנחנו רוצה שנשב את זה ונסכם המשך העבודה שלך עכשיו, אנחנו צריכים להתכנס בסינגרה. זה משנייה חשוב, אני רוצה